Okay, all right. Need to do the, oh, hang on. Can I mute this laptop? Yeah. Oh no, is it functional? Oh no, shit. Okay, cool. All right. Okay. Hi, everyone. Hello, hello, hello. Hello, hello, hello. Woo, woo, woo. If anyone sees my mouse pointer, if they could let me know. Oh, there it is. Okay. All right. Thanks, everyone, for coming. This is great. Great turnout. We've got this is our second, I guess it's technically our third deep tech meetup, but the first one was just a bit of a social event. Last time we had a health tech, med tech startup one, and this time is all about space. Cool. And then we're always looking for speakers, of course. So if you've got if you or you know anyone that might be interested in talking, do let us know. Yeah. So just want to obviously acknowledge. Sorry, my mouse pointer's on the wrong screen. Do you want to? Why? Oh, sorry. This is so amateur hour. Do I tech? There you go. That thing's on that screen, but this thing's on this screen. So I just want to acknowledge the traditional owners of the land on which we're meeting today, the Wurundjeri people of the Kulin Nation, and pay my respects to the elders past, present, and emerging. And with that, I want to introduce today's speakers. So we've got Sho from ESPA, who is not here yet, but assures me he will be here soon, so that's cool. And Tenzin from Element Robotics, and he'll be up first. So if you could give Tenzin a warm welcome, and we'll dive straight into that. Yeah, let's figured if you put it around there, that's probably best. Cool. All right. That was probably a horrendous sound for her visitors.
Yep, sorry. That's what happens.
Give me 1 second, I'll just switch to me.
I may have disappeared my screen sharing here. There we
go. All right.
I'm ready.
You're ready.
It should work. All right, I'm going to introduce myself while we're waiting for the technology because you don't really need my slides for that. Thanks everyone for coming. My name's Tenzin. I'm a robotics nerd. I spent the last couple of years in the US working on a micro rover called Moon Ranger. It's a mission coming out of Carnegie Mellon University. So I'm going to talk a little bit about that today. And then also spending the next couple of years of my life at least working on the Australian Trailblazer mission, which was announced, the consortium winners were announced for that recently. So I'll talk a little bit about that today.
Just realised it's slight technical.
Sure.
Is that you need to share your screen to that thing.
Oh, cool. Excellent.
You say is it only Wi-Fi or does it do
It should be Wi-Fi, right?
Yeah, it's on Wi-Fi. Can you? I don't know how your Windows thing works.
What is it on?
If it's on this network, it's called the Samsung something like that.
Oh, I see. I see. It'll be fun. Give us a couple of minutes. This will be fun.
Talk amongst yourselves.
I
thought there was another thing I hadn't thought of.
No, my presentation. I can probably do. Cool. So you need to cast, or I can try.
Try from the Google Slides.
I was about to say that. I was going to go this. I wasn't in Google Slides, but I can be in Google Slides.
Sorry about that.
So
Can't do presentations. Definitely can launch stuff to space.
right, can put rover on moon. We're currently casting through the YouTube stream through his laptop to that screen. So
This is a 10-second display.
it's kind of like the round trip time to the moon. Anyway, so all right, I'm talking about lunar rovers. I was talking about what I've been working on. I've spent a bunch of time doing robots. I don't need more of an introduction. So, oh, this is going to be fun. Let's see how long the delay is.
It's massive.
Okay. That might be awkward. No slides? Yeah, I tapped it earlier. All right, so I'll tap it. This is the presentation. We've already heard about who I am. What I'm going to be talking about is kind of a combination of historical work that I've worked on and future work that's coming up, a bit of both. And then feel free to ask questions probably towards the end. If you're entertained, I asked someone, you can guess who, to generate a picture of what an amateur chef, sailor, and salsa dancer is, and apparently you can be all three at once. Thank you to generative AI. Yeah, pretty stylish, yeah. Salsa dancing, you're talking about? I didn't say style, no, I just gave it those keywords. That's all. So I'm going to be talking about the moon. And someone already in the audience asked me, why do we care about the moon? So that's a great introduction to the first part of the presentation. We care about the moon for a number of reasons. If you think back 50 years, you know, we had the Apollo missions, we had a pretty exciting drive towards getting to the moon. And if you think back even longer, we've always been like, oh, look at those stars, that's awesome, right? So we're pretty excited about it for a while. And we went to the moon, we got some information about the moon, and we're like, okay, we've kind of had enough now for a number of reasons. But I think we're at a point where we're ready to explore the stars again. And there's a number of reasons for that. We have some massive advances in launch technology, and we have some real excitement and sort of competition around driving technology forward. You can think about that in a number of ways. I think there's three core reasons we want to go back to the moon. We want to go back to understand a bit more about our universe and what that means for Earth and the rest of the solar system and beyond. We want to go back because it will drive and stimulate development of technology. That is not just technology for the moon, but also technology that can be used here on Earth and anywhere else we might want to go. Some of those things might be habitats or new power systems, those types of things. And all of that, you know, comes down to maybe there's an economic opportunity, both in using things on the moon. Maybe we'll find future resources there that might be applicable to Earth. One popular one that people talk a lot about is helium-3. And there's also economic opportunity for exploring that beyond that and helping things happen here on Earth as well. As I'm going to forget to press the slide too early, this is going to have some really interesting transitions. So I think the really important message, though, is there's a lot of serious reasons why we want to go back to the moon, but we all just want to go back because it's cool. Like, that's like the only way we want to go back is because it's cool. I don't know, I kind of had this realization while working on Moon Ranger, which you can see a little tiny picture of on top of the moon. Like, stuff I've touched is going to be 250,000 kilometers away. Like, that's kind of awesome. So hopefully I can share a bit of that excitement with you guys tonight. So going back to the moon is a big challenge. A lot of people are working on it. There's people coming out of Japan, US, obviously, China, India, Australia, UAE, a lot of that area. But how are we going to get there, and what are we trying to do? I think the sort of core drive at the moment is we want to put a permanent presence on the moon. We want to establish a settlement there. And so how are we going to do that? Because humans aren't really designed for space. These organic matters and vacuum kind of not so good. So we need to sort of figure out options like robots, and what are they going to help us to do? Well, first, kind of like when we first explored places that we didn't know, things like Antarctica, we go out and we find where things are. We're going to make a map. We're going to maybe take some photos from outer space, get an idea of where it is, and go in and get a more detailed map. A lot of exploration activities. Robots can help support that. And once we go beyond the support for exploration, we need to get into this capability to build things and create things on the moon. Because even though the new launch capabilities have enabled us to send rockets a lot cheaper and a lot more frequently, it's still pretty impossible to send everything you need from Earth all the time to sustain a lunar settlement. So robots will help extract and also process resources construction, and eventually also support base maintenance. So this is some concept art that I found online, which I actually think is a pretty good idea. We probably want to build some landing pads. We're going to do some mining, have a power generation system, and we're going to have some habitats, which you can kind of see in the background. Okay, so obviously I'm wearing a t-shirt that says Element Robotics. I am currently the co-founder of Element Robotics. We founded this company because we realized we can't continue to build space robots the way that we've previously built them. And that way is typically, we come up with a bunch of science payloads, we design a mission around those science payloads, and then we build a robot that meets the specific requirements of those payloads. Then we repeat that process for a next robot. We might use a little bit of inference. So if you see, repeated designs of Mars rovers, there's a lot of similarity, but it's still a new mission and there's a lot of non-recurring engineering costs. So that means that every mission that we send is really expensive and doesn't take advantage of the opportunity to reuse a lot of the materials, technology, and design. So we wanted to come up with a way to do that. And coming out of Moonranger, we said, wow, we've got a bit of an idea about how to build micro rovers in particular. And someone asked, what's a micro rover? I don't think there's a specific definition for a micro rover. I'm saying anything under 100 kilos. Maybe there's a size constraint as well, but this is sort of a size that you can send on a rocket now that would go on a lunar landing company. That's something built by the Commercial Lunar Payload Services contracts coming out of NASA. So it's fairly small, maybe size of a couple of chairs size rovers. So we wanted to build, take the technology we saw on Moonranger and turn that into something that could be used on other missions. So that was the focus of building an autonomous rover platform, and that's kind of our core focus, particularly the software aspects of that. But to do that, we also need to support building a lunar simulation environment because we don't really have enough data to be able to test rovers in their full capacity. We want to do that. A lot of the open source simulation environments and tools that NASA have are very limited mission specific. So we want to try and build that capability out so we can help a lot of the different rover missions. There's also a bunch of challenges in building space things, particularly around hardware-software integration. And based on that, we're looking at some ideas in development and testing tools as well, which there's a tools underneath my name over there. So anyway, so yeah, a little bit of history. I'm going to talk about Moonranger. Moonranger is an 18-kilogram autonomous lunar rover. It is designed, built, and tested at Carnegie Mellon University on contract from NASA. And its goal is to search for lunar ice. So that's a picture of an engineering model of Moonranger. It kind of, when it's set there, it's about that high. That's the top of the solar panel. And when it's folded down, it's the size of the height of my laptop, maybe a little bit higher. There's a few different things about it. It's designed to go for a single lunar day. So typically, if you look at the missions that NASA has put out before, they are long duration missions. Some of them were only designed to go for maybe 90 days, some of the Mars rovers, for example, but they went on for years because of the sort of engineering design and rigor behind them. In this case, micro rovers typically don't have enough capacity to keep warm during the lunar night. So the current sort of technology, unless you're using radioisotopes, which you have to be like military and US government to do that, you don't really have enough energy from a solar panel and solar power and current battery technology in the space that you have in a micro rover. So that's why the single lunar day mission. As I mentioned, the Moonranger maps for ice, and I guess the other exciting thing is we're going from a mission that costs billions of dollars to a hardware cost of under $1 million Australian dollars, which is still expensive for you and I, well, at least for me, I don't know about you guys, but it is not impossible, right? It's something where we could send multiple of them. We could send one and have it fail and iterate on that design. It's sort of more of this more modern design philosophy. So I give you some eye candy. This is actually a picture of assembling the flight rover. It's very busy, nothing like the clean picture you saw before. Even though it's tiny, there's a lot of stuff you need to cram in. This, in this case, is upside down on a bench with the solar panel at the bottom. We built a carbon fiber chassis laid it all up ourselves at the university. And that was both a structural component and also a protective component, obviously. Inside this aluminium box here, we have a flight computer, sort of a high reliability computer, and a lot of electronics that were built in and designed in-house. And the aluminium casing is designed for sort of thermal management, but also protection from radiation. That's a challenge for electronics in space. Down the front, we have some navigation cameras. Again, we have the advantage of an atmosphere on Earth, which means that we disperse light and you don't get sort of these stark contrasting shadows. On the moon, you can be in a place where it's really, really bright and your camera will get washed out as if you're pointing at the sun. And then right next to it, you have a spot that's really, really dark and you can't actually see anything because there is no dispersion of light, or extraordinarily little. So we had to design a system to manage that. And we'll see how effective it is. We think it's pretty good, but there's always a challenge without having actually been there. We want to have an autonomous rover for a number of reasons, primarily for speed, because we want to complete a lot of things in a single lunar day mission. So we need a computer to do that. For anyone who's an electronics nerd, inside that box is a NVIDIA TX2i, which is approximately 1,000 times faster than the computer that's running the Mars rover. So that has teraflops of capacity. The Mars rover has gigaflops. So it's a huge step forward. And the reason we're able to do that is because we have such a short duration mission. The amount of radiation that this device can sustain is sufficient. It has enough protection to survive like a short term mission. It will be much harder to do that for a longer mission like the Mars rover, and that's why we have this capability. And last but not least, right in the middle here, probably a little bit hard to see, is the NASA Science Instrument. It's a neutron spectrometry system. I'm not a particle physicist, so don't ask me exactly how it works, but something along the lines of bouncing hydrogen particles from solar wind. Some get absorbed, some get reflected. You can tell how much hydrogen is in the ground, or water ice is in the ground, by the difference in measurement on two tubes in there. So basically an anode and a cathode, super high voltage. There's only 4 of them in the world, and we got to play with one of them. It's kind of pretty exciting. The other one is going on one of the NASA rovers, and then one is already in space, and that's where we got the idea that actually there might be water on the moon. So where are we at with this? Moon Ranger is almost ready for its mission. We started in 2019, went through preliminary design review, critical design review, and coming up to systems integration review, which was scheduled for the end of last year, but had to be delayed for a couple of reasons. One of which was we needed to do some more testing and improve the electromagnetic interference of the rover. And the other of which is that Moon Ranger was on the Commercial Lunar Payload Services Mission 19 Charlie, which was run by a company called Maston out of California, or Mojave Desert, and they went bankrupt. So we no longer have a mission manifest for the part going from Earth to the moon. And this is kind of something you'll see a lot in space. Missions get delayed, things go wrong, and you kind of have to deal with it. So we are looking for alternatives at the moment where we will fly. Basically, this was a contract to NASA. NASA has the rover, and they're like, we're ready to sign off on it as soon as we have the integration with the future lander. It may be on a future Commercial Lunar Payload Services mission that comes up, or it may be on one of the Artemis missions, which will be a whole nother challenge because that involves human spaceflight. This is actually a picture of the flight article when we were wrapping the multi-layer insulation gold blanket around it. It's a super fine foil and some Kevlar. So pretty cool. Obviously inside a clean room. For anyone who's a medical nerd, it's not a medical grade clean room. That's why we're not wearing like face everything. So what's next? The exciting stuff to talk about is what's coming up in Australia. So I'm not sure how many people are tracking, but the Australian Space Agency a couple of years ago now announced the Moon to Mars Trailblazer program, which is designed to support NASA by building a foundation services rover, which will collect regolith, lunar dirt, and deliver it to an in-situ resource utilization facility that they will provide on the same mission. ISIU stands for in-situ resource utilization. The goal here is to stimulate sort of Australian industry and get everyone excited in Australia about building stuff and going to the moon. I think it's pretty awesome that we can finally do that here. We have a space agency now. It's amazing. Thank you to the people who actually got around making one. Yeah, super excited. And the planned mission for this is in 2026 on a different NASA Commercial Lunar Payload Services mission. The exciting thing about this, it's Australia's first lunar mission, and about 2 months ago, the 2 winning consortiums were announced for that stage 1 of that grant. One is the AROSE consortium out of Perth, and the other one is the EPE and Lunar Outpost consortium, which is primarily based here in Melbourne with a few offices on the East Coast. And there's a couple of Lunar Outpost people in the audience as well. So that's really exciting. Element Robotics is part of the Lunar Outpost consortium. We'll be writing the autonomous navigation software for the rover. And yeah, we're super excited to sort of bring the technology and experience that we had on Moon Ranger to a similar program with a new mission now, which is to extract regolith and put it into a in-situ resource utilization facility. This is a picture of the consortium where everyone is. you can see a bunch of people there. RMIT's about a few universities, Lunar Outpost and EP are the primary grant recipients, and yeah, Element Robotics down the bottom. So what is stage one? Let's talk a little bit about that. Stage one is going from the mission concept component. So we have a bunch of requirements that were listed in the grant proposal, including get some regolith and put it somewhere, which is basically the primary requirement. And then we need to translate those into a concept for mission. Like, this is our rover, this is how it's going to operate, this is what it's going to look like. And then we need to translate that through to a preliminary design and sort of initial prototype. So that's phase one. At that point, the two consortiums will sort of compete with each other for the best design, and that will be down selected by the Australian Space Agency for the phase two to build the actual rover and go to the moon. So we're obviously trying to make the best rover, and we're going to make the best rover because we're the best. But yeah, super excited to be involved in that. And it's happening here in Melbourne, which is, at least some of it will be happening here in Melbourne, which is kind of exciting for people in this room. And then the only other thing I wanted to say was, it's pretty exciting to look at where we're going. Maybe we can imagine a future where instead of sitting in this room talking, we're looking into deep space and thinking about where we might go next. Maybe from our settlements on the moon and Mars, with our plethora of robots supporting us, we might be able to go into different parts of the solar system, or even to another solar system. That'd be kind of cool. I think we'd learn a lot. I'm super excited about it. Hope you are too. And yeah, I'll take any questions. Yes.
So you could apply like a disposable rover, just one day and then.
Yep. So all of the micro rover missions to date don't have essentially a thermal capability to survive the night. Everything else is fine. It's just the thermal capability. There are some pretty interesting things happening in that space, like self-inflating pop-up tents is one, kind of cool. And there's also some really interesting materials that are not nuclear radiation based in terms of supporting heat at sufficient densities of batteries to survive the night.
So then, do you know what light ever also costs? The per unit is less than $1 million.
Yeah, so the I don't know what the launch cost is. The typical cost for a commercial lunar payload services lander, like the spacecraft. I probably should have explained this. A rocket could be a SpaceX rocket, could be something else. Launches a spacecraft into Earth orbit. Spacecraft translates to the travels to the moon, drops on the moon, stuff drops off, or they do science on the moon. So there's kind of three components there: rocket launch, landing craft, and then payloads, whatever the payloads are. In our case, rovers. For the landing craft, contracts are around $150 million US, and they usually have a lot more than just a rover on them. So, is it cheap? No. Is it cheaper than what we've ever put on the moon before? Yes, by a factor of 10 or 100.
The concept that you can have a whole bunch of these.
Yeah. So for NASA has, I can think of 7 on-contract commercial lunar payload services, and there's plans to have 2 or 3 more every year. If anyone's tracking the news, the Japanese iSpace is basically a similar sized landing craft. That was the one that tried to land 2 weeks ago, someone who's tracking news, and crashed. And there's a couple of companies around the world. Bereshit 2 is another mission coming out of Israel, and then Chandrayaan 3 is another mission coming out of India. Similar sort of size.
What will happen to them? Will they just live there forever?
I guess so. I suspect what will end up happening is when we get to the point of having a lunar settlement, they'll start reusing the materials. I also don't know that, well, it's interesting to think about which technologies are going to break from the cold. Batteries is definitely one of them. But if you were able to supply power from something else, then I don't think, maybe computers will die from radiation. A lot of time. Yeah, lots of isotopes. Yeah.
You mentioned before, it had like a graphics card that was like computer power much more than Mars rover.
Yeah.
I think you may have mentioned different batteries, but like what you're doing up there with more computation.
Right. So we would, yes, we have the opportunity to be able to do that. Mars rover does drive pretty autonomously, so they've been able to strip down the autonomy algorithms pretty well. We have the opportunity to do that. primarily because of the mission duration and total radiation. So the sort of general principle goes, the smaller the computer architecture, so we're talking about silicon wafer size and chip size, the more likely it is to get affected by radiation. So you need to find the right balance between the amount of radiation that your device can sustain for the particular mission that you're working on, and the compute power. And typically, you'll find for a lot of the bigger, longer duration missions, they end up going to field programmable gate arrays or FPGAs because they have the time to develop custom algorithms for each of those, and it's a much more robust architecture. But if you're trying to do something quick and fast, it's really hard to get all your autonomy algorithms on an FPGA. Yeah.
Could you just insulate the computer? Like with
Yeah.
FPGA?
Yeah. So this is basically what you do. You put as much as you can on there. We were calculating 2.5 millimeters of aluminium around the entire, like all of our structures. Unfortunately, there's this problem of like weight trade-off. So we were very close. Like for context, we have 2 kilos of wires on there, right? All the things you don't think about, and suddenly your weight is going up. We actually had to cut the wheels down to be enough to get us within the weight margin. Like you're trading grams here, right? And so at some point you say, what's the duration of mission? Okay, how do I protect from radiation? Can I use some fancy materials, that sort of thing? So it's a trade-off. Cool. Yeah.
Do you think like Starship is going to be a game changer?
So Starship is 100% going to be a game changer. So for context, when we get the launch capability of Starship, we're going up like 100-fold in weight capability to get things into space and to the moon particularly. Maybe it's even 1,000-fold. I mean, I have to calculate that. I haven't actually looked at it, but it's a massive, massive change. Yeah. And even anything that's close to competing is like, so the latest like rockets out of Blue Origin, 1/10 the size of Starship. Even. It's 1/10 the cost as well, so it's a trade-off there. Yeah, so the Trailblazer mission, well, both the missions that I talked about today will be polar because they're looking for areas where there is likely to be ice. And that's from the previous missions that measured from like an orbit around the moon. The specific location is very dependent. The Trailblazer one is not, to my knowledge, disclosed. I don't know. We know it's polar. That's about it. And then the one for Moon Ranger, we were actually part of the selection process for the area. It was an area called the Hayworth Crater that we were looking at, and that was a combination like where is it safe enough to land? There's not too many big obstacles. We should be able to get a lander in there, but it's close enough to things that we want to be interested in because unfortunately the areas where we think it's interesting scientifically are also not the best places to land your spacecraft because they're typically got lots of craters and all these things. So you want to be close enough, but not too close, and sort of go through this process. You also have to think about the lighting conditions. In the polar region, the light doesn't really go above. It's kind of like being in the northern territory, like right in the north or at the South Pole. The light's always on the horizon. And so you want to think about, am I going to get occluded? Where am I going to get occluded? Do that analysis as best you can with the data you have available. Yeah, so the data comes back typically through the Deep Space Network. So essentially you have a ground station here on Earth, and that connects to a series of satellites. The primary one for long distance space stuff is Deep Space Network. It's a commercial network, sort of commercial network. It's very low bandwidth, like we're talking about 0.5 kilobits per second up speed. We were expecting about a 20 kilobit per, 20 kilobit per second down speed. So you have to adjust for that in your calculations. Not what you're used to with your fiber optic cable, but that's basically how it works. And then the lander acts as a beacon for that and broadcasts Wi-Fi to the rovers, actually. Slide note, because people are nerdy, when we were looking at Wi-Fi, obviously Wi-Fi has never been used on the moon before. If you ever set up a Wi-Fi router, you have to select a region. So how do you select the region? And at some point, there was an application that went to the FCC to say, we need to put a Wi-Fi on the moon, which region should we use? And there was discussion about putting a moon region in the Wi-Fi standard. So just saying, if you see a moon region in the standard in a couple of years, you heard it here first. Yeah.
How mature is the software ecosystem? Is there some amount of reuse and collaboration, or is
right.
More ad hoc?
So most of the previous missions that have actually flown are either completely commercial stuff that's flown on satellites and you have to pay exorbitant license fees for, or are not applicable, right? Because it's a satellite, not a rover. Or they're government. So they might be NASA missions, and depending on who you are, you might get access to some of that. A lot of the people that I know who are working in this space are basically trying to use research-grade robot code, so think robot operating system code, to build these, and that's what we did for our prototype. But at some point, we kind of said, it's not stable enough. We need to move to something else, and we moved to something called Core Flight Systems, which is an open source framework that NASA is providing for satellites and a bunch of other things. It doesn't have any of the autonomy stuff in there, and you have to kind of build that in. We had some challenges doing that. So I guess the kind of answer to your question is there's not really a broad consensus on exactly what to use. I think space community is tending a little bit towards core flight systems. There is a small community looking at space ROS, which is basically how to make robot operating system version 2 a little bit better and reliable, specific for the space environment. Don't know exactly which way we'll end up going in the future.
Just thinking about reliability, a lot of areas systems
Right. Yeah.
Is that something?
So we didn't have the weight, basically, to put redundancy in. We ended up with a two-computer architecture. Partly, the original argument was partly for redundancy, but when you do a real analysis, you actually, this is not really redundancy. Like, we go from having a capability of driving around autonomously to maybe having a capability to get like critical sensor data back. Like, it's a very different functionality rather than a redundancy in that sense. I think there is value in thinking about redundancy for some aspects, but in a size mission like this, it's extraordinarily difficult to get the redundancy you need in the weight constraints, basically. Yeah, weight is a huge constraint here. So you might not have noticed, but the rover doesn't have like a suspension system, right? This is really, really bad for driving, and we had to do a lot of testing to prove that. We just didn't have the weight for a rocket, right? Just didn't have it. Yeah.
How many days is a single?
Yeah. Yeah. Yeah, so we're planning for 14 days. It's the usable light is actually a little less than that, but yeah, 14-day missions is typical for polar region if you time everything correctly, right? Which you try and plan to do. You also have to think about when you're going to send your rover in terms of a radiation cycle, right? So the solar flux cycle affects the amount of radiation that you get as well, transiting to it. So that actually matters. Cool. I probably got, yeah, taking way too long time.
I was just going to ask you a question. At the end, you have to make sure that you park the rover.
This is actually a good question. We didn't have that constraint imposed upon us, but I'm sure that as we get more missions, they will be more specific about where you put your assets because it's going to get crowded. Yeah, for sure. Right.
Okay, awesome.
All right. Thanks.
Well, thank you, Jesse.
No worries.
So if you just give us a few minutes to connect show, because I'm sure we'll have some of the same problems.
You're right.
Okay, all right. Okay, tech issues sorted. Ish. We're gonna have to do the same thing again. It's a Windows issue. Okay. Next up is Show from Esper. Give him a round of applause. Thank you. I'll just put this on you somewhere. Yep, sounds good. Okay.
Yeah, let me get on that. Ooh, there we go. Alrighties. Well, hey everyone. Sorry, I was a little bit late showing up, so I couldn't really socialize at the start. But yeah, I'm Sho. I'm from Esper Satellite Imagery, and well, as it says, we're a company that's trying to save the planet through data. Basically, what we do, or I guess what we're looking to do, is I forgot to delete. We are so this sort of goes back to how in prehistoric days we used to look at the skies, we used to look at the stars and use that for navigation, for weather forecasting, and basically using the stars to guide a lot of our principles as human beings. So we're doing something similar, but now in terms of using, I guess, the stars or space in general to sort of look at more challenges that are facing the Earth, more from a climate perspective. So essentially, we are building hardware, launching it up into space, and using that to track climate metrics, climate data, for very specific industries. Again, just waiting for the slide to change. But while it does, we're looking at everything from resource management, all the way to everything like forestry and agriculture. So some of the things that we're looking at are methane leakages. So oil and gas companies, coal mining, and a lot of these things, they release a lot of methane from everything from whether it be the pipeline that's carrying it, because methane is still a natural resource. It's natural gas. We use it for our homes. We use it to basically stay toasty. But it still is also, around 80 to 90 times a lot more potent than carbon dioxide. So which means that it traps a lot more heat than carbon dioxide, making it, again, a deadly greenhouse gas. So we're looking then beyond that as well. We're looking at mineral exploration. So mining, has this entire area around it where we know that there is a huge environmental impact of it on the planet. But then we are also reliant on it more than any other resource-focused industry, minus agriculture. We need mines. We need mines to get our iron, get our steel, get the stuff that goes into our electronics, into our batteries. And mining is basically what's really powering the next gen green tech movement. Everything from newer battery technologies all the way to electric cars, all the way to more efficient building practices and just sustainable infrastructure in general. A third area that we're looking at is more along the forestry / agricultural side, where we're looking at carbon capture. So instead of basically instead of helping other industries be a lot more efficient, this is where we're directly making an impact in terms of carbon reduce in the actual atmosphere. So we're helping track carbon that is sequestered by forests, by coastal areas through seaweed, and basically agricultural land as well, where farmers and forestry reserves, all the way to farmers of seaweed, actually get paid out to plant a lot more crop to actually capture a lot of carbon from the atmosphere. And we're building the data systems to be verifying a lot of that, to actually have a proper, a more positive impact on the environment by helping reduce carbon dioxide in the actual atmosphere. The way we're doing that is we're building and launching satellites into orbit that can track all of these chemical metrics. So we're building hyperspectral sensors. So these are sensors that they capture light in hundreds of different wavelengths. So not to get all physics on you, but we're basically doing spectroscopy on a macro scale of the entire planet. So we're capturing light in hundreds of these wavelengths deeper into the infrared range. We're utilizing all of this information to look at chemical absorptions and reflectances. So every mineral, every material reflects and absorbs light differently. We're basically able to look at the entire spectrum. We'll look at where it's absorbing, where it's reflecting, and basically look at its spectral fingerprint. So spectroscopy is fairly commonly used in a very small lab environment, but now we're doing that for the entire planet on basically a square kilometer level everything from the columns of the atmosphere to surface level data. So we've been working on this stuff for the past 4 years now. Started it off as a university side project. It was just me and my co-founder. We met in our first year of our engineering degree. In our second year of our engineering degree, we ended up going to a hackathon which we ended up winning. That's how we sort of got into hyperspectral tech, and this is actually one of our first prototypes that we built. So we took his dad's DSLR camera, put this entire so there's like a bunch of PVC pipes here. A couple of off-the-shelf Canon lenses, and basically for the first lens we capture a lot of light in. We focus it onto a diffraction grating. Essentially, it's a prism. It's the same concept as a prism, but it's a film. We focus it through that, and there's goes through another PVC pipe to again go through the main actual imaging lens or a proper camera lens to basically look at these really fun rainbows that we end up capturing. So on the right is also like the first hyperspectral image that we caught. It was just a banana taped to a door. We were trying to get creative. Instead of taking pictures of fruit baskets, we were like, yeah, let's just tape a banana to a door. So we sort of built our first few sensors around the same concept. It was still a university side project. We were just working on fun. And hopefully trying to see where it goes as a business, and looking at a lot of business cases. So we were at Monash at the time. I think this was while we were at our second year of engineering degree. Was it third? Yeah, it was probably third. And that's how we sort of graduated to working in as a side project to working on it full time, but outside of Joey's kitchen. He's my co-founder. So that's us building our second sensor again on his kitchen countertop. So similar concept, we just made it a lot smaller so it could fit inside of a 3D satellite, 3D CubeSat. That was us still sort of working out what we eventually wanted to do, as we were still playing around with the technology just because we thought it was cool and it was fairly accessible, at least the way we started engineering it. So we worked on this prototype for a bit. That's around the time that we raised our first bit of funding, mostly family and friends. Then we ended up getting a manufacturing grant from the Australian government as well. That's when we really got around the business cases that we actually want to be focusing on, rather than just building cool cameras and launching them into space. Now here's a few pictures of cool cameras that we'll be launching into space. So graduating from that first or that second iteration of that sensor, we've been building our first space rated module. So completely strays away from the initial philosophies or engineering philosophies that we're really looking at from the first few prototypes. We designed this from the ground up to be surviving the space environment. So everything from aerospace grade materials to internally, we were still using a lot of off-the-shelf optics to be developing that entire focusing all the focusing optics to the prism optics, then focusing it again on essentially an image sensor. And yeah, that's basically what this sensor essentially does. So these two images are from our space qualification test. The one on the left is from our thermal vacuum test. So right behind that, you'll see this entire stack of computers that we have there. So we're working with a company called Spiral Blue. Some of you guys might have heard of them. They make space edge computers. So these are computers specifically for payloads like ours, for Earth observation payloads. And we're using them to do all sorts of like software stuff on the actual sensor data that's coming out before we actually downlink it, just because it's tons of data that we're generating, because we're capturing hundreds of wavelengths instead of just 3, which you would be normally doing with like a normal RGB camera. So we're using their platform to do everything from payload control all the way to doing a lot of onboard analysis. So what I mean by that analysis is that when you capture images of the Earth, around 40% of the Earth is always covered in clouds. And if you're in the visual spectrum, which these sensors currently are, that's basically useless information. You don't want to be downlinking that, because then again, that becomes a cost to running the actual satellite up there. So what we eventually end up doing is run the algorithms to look for clouded images and delete them, just because we know they're not that useful. The image on the right is us doing the vibration testing of the actual thing. So again, making sure it survives the actual launch environment. The same thing was with the TVAC testing as well. So these are fairly recent photos. So our TVAC testing last December, and the vibration test was, I think, 2 months ago now. Last week, we delivered the first sensor to our launch provider. So we're launching on 2 satellites this year. One's going up in October, and the second one is going up in January. So we delivered to the January launch before we did for our October launch, which is weird. But yeah, this is the actual sensor inside of the actual compartment we will be in when we're on the satellite. So it's basically a 3U CubeSat deployer, which is now being repurposed as like an entire hosted payload compartment. So for those who don't know what hosted payloads are, we basically, as a payload, we buy space on other people's satellites. They give us everything from whether it be logistics to the launch logistics, all the way to all I guess the in-space logistics we need to actually get the data down off our sensors once they're actually out there and capturing. So that's what we're doing for our January launch. The second launch, however, is a more dedicated satellite. I don't have a picture of it, but I do have it on the back of my hoodie. So yeah, I love this merch. So that's the satellite we're flying on in October. So that's an entire 30U satellite. So basically, yeah, it's a little bit smaller than a mini fridge. And that's a completely dedicated mission for us. Launching in October on board an ISRO rocket. This payload's going up on a SpaceX rocket. Yeah, essentially it's fairly cool imaging technology that we're building and launching. But a lot of what we're still focusing on while we're building cool hardware is still looking at a lot of the climate problems that we're working with. So everything from carbon sequestration to carbon monitoring, and I guess mining sustainability is a really huge pillar that we've based a lot of our technology around, just because that's being local in Australia, that's around 30% of our exports, and that is just a really closer story to us. Especially as we sort of get deeper into, I guess, the developments that are happening in climate tech, they all rely on critical minerals and all the technology that's coming from that. And we want to be an enabling technology to basically make that entire supply chain as sustainable as it can be. So yeah, that's sort of about us. I feel like I rambled a little bit here and there, but yeah, just wanted to show you guys a few cool pictures of the stuff that we're working on. I'm happy to sort of dive into different parts of whatever you guys find interesting.
Do you do any data processing? I assume you sell that data to
Yes, we do.
ad companies. Do you do any pre-processing, or you just kind of give them the raw data?
Yeah, so we are primarily positioning ourselves to give the raw information available, but we still do some pre-processing on the actual data. So to take a step back, like the raw sensor information that we capture is not something that you can plug into some GIS program, or have somebody look at it and be like, oh yeah, here's carbon, or here's XYZ, right? There needs to be a lot of work to be done on the data before it's even like ingestible, even by a software program, let alone our own eyes. So we do some of that ourselves. So everything from making sure all the data looks clean, because we're capturing it from space. There might be radiometric corrections. Sun might be too bright that day, which means that we need to account for that and reduce the brightness of our images and do a lot of those corrections, and geometrically as well. Let's say if because we won't be always looking straight down at the Earth, we might be looking at some different angles. That might mean that some pixels might be further away from the actual camera than some other pixels, so we need to correct for a lot of those things. So that's a lot of the processing that we do in-house to actually make it something that a company can buy and start ingesting into their own data systems without doing a lot of that stuff, because that is, again, very specific to us knowing all the telemetry data of, I guess, what we're working at, of the actual sensor and where it was in orbit.
Do you need to qualify that data and confirm with other ratings?
We do. So essentially that happens in like the first 2 months of the actual satellite launching. So we do calibration of it in orbit. There are, I guess, different sites across the globe or control points essentially, which have a known spectral radiance, and depending on different orbit altitudes and those sort of things. So we know if we look at it, what we're expecting to get, and versus when we look at our own data, we can tune it and calibrate it to actually capturing, I guess, spectrally accurate data. Of course, we do a lot of the calibration on the ground before we actually set it up, but that's the in-orbit calibration is probably the most important step when it actually comes to making sure our data is spectrally accurate, and from a geo point as well. Those are, I guess, the control points that we use. It really gets hard when we're capturing over oceans because, well, oceans are flat, plain, unless you're just looking at waves, right? So it's really hard to determine between different images and where different points are. What we're thinking of doing is capturing a ton of data from one shore to the other shore, and then using those shores as control points to, I guess, make the entire data strip that we're essentially capturing basically geo-rectified. Planet Labs does this, and for us, it might be a really big stretch just because, again, we're capturing 100 times that information. So we're looking to figure out better ways of doing that, but for now, that's the only solution that I guess the industry knows of.
What's that area of the Earth?
Yeah. So we are a push broom sensor, so that essentially makes us a line scanner. So per each capture, it's, I guess, different. Width-wise, so we're capturing like 8.5 kilometers. So it's fairly narrow compared to what's already out there. Like I think, Landsat and a few of these satellites are like 15 to like 20 kilometers in their entire width that they end up capturing. We're only 8.5. Again, it's a smaller sensor. We're trying to pack a whole lot of technology in there. We're capturing like 100 different wavelengths from visual to like touching near infrared. So for this size sensor and I guess for the quality of data we're actually capturing for the cost, it's I guess really, packed a little bit too much in there, which we're trying to work around.
I have two questions. The first one is just on the topic of capturing 100 times the data. What's the effect of time of capture in the sort of capturing process? I guess you have to think about that.
Yes. So it really limits so that means we can only task the images. We can only tell it what to capture instead of always be capturing. So ideally, we want to be, always be capturing the Earth, monitor every single point on it, even if there's nothing happening. But because, again, we're generating all of this data, which is, putting a whole lot of cost on the actual, obviously from a monetary cost, but also a hardware cost because it's taking up all that bandwidth. It really makes us pick and choose areas where a customer is actually paying for that. So yeah, while we want to be capturing the entire Earth, then hopefully we'll get there one day, and that's what we're working towards from a huge computing point of view. But for now, it's just we need to be told where to capture, when to capture, and that really, I guess, again, and that's again, the customer is limited in some sense because we need multiple satellites up there to be doing very broad scale captures at fairly frequent intervals. And that also puts again strain on us where we're using up a lot of the bandwidth that's available to us up there.
You briefly, like in 2 slides, you went from this really cool looking prototype on a kitchen bench to I'm doing a vibe test on an optical sensor that's going to space. There's a lot more to that story. Do you want to sort of talk a little bit about like what you had to learn about and figure out?
Absolutely.
That's
Absolutely. Let me actually good point. Yeah. So funny thing we learned is Canon lenses do not survive in space. Yeah, I was surprised. So there's when putting things in space, especially when working around with optics, there's a huge concern around outgassing of different elements of the actual system. So that because essentially if you fog up your lens, the data you end up capturing is useless. You spend hundreds of thousands of dollars developing this payload, and it eventually ends up being, again, useless. So going from, I guess, our second prototype that we were building, we were still using a lot of off-the-shelf equipment, everything from, again, these Canon lenses and stuff that worked great because we didn't have to engineer our entire optical system around that. And we're working off of, these lenses that basically correct all the images for us as we could end up capturing. Once we sort of moved to space, we can't really use any of them. We had to completely scrap the design that we were working on, that we basically worked on for a year and a half, in favor of the actual space grade design. So again, going to the spectrometer physics, we were still looking at a lot of the same, I guess, principles, but we ended up having to completely scrap a lot of the parts that we were using, a lot of the engineering effort that we went into it, and in some ways completely start from scratch. So we had to, first of all, we had to like select materials that would actually, from an optics point of view, that would work in space and actually capture good data. And that's how we started, doing a whole lot of simulation. It started with a bit of simulations where we were like, all right, there's 100 of these spectrometer concepts out there. We worked with a few of them, then we basically started simulating, all right, what is, gives us the best data quality for, I guess, stuff that's available to us on hand. Because we still had a very limited budget because we were still at uni while we were building these. So under a few $100,000, while paying the entirety of our staff, how do we develop a space grade sensor which does a lot more than what any other sensor of this size has done, while staying under that budget, and that was like one of our biggest engineering challenges. But that's of course now become a huge competitive advantage for us as well. One of these sensors, while it's space rated and it's capturing so much more data, it only costs us like $20,000 for us to build. So that's on a grade of like a space hardware that we can build one of these every 6 weeks and launch these for like a few $1,000s on top of that, a few $100,000 on top of that. But yeah, one of these like hardware articles like really costs us a lot, a very less amount of money to actually get these things up into an orbital condition. Yeah, it was completely going back to the drawing board and starting. All right, we know how the technology should work. Now it's like, let's start this from scratch. So technically, this is V1 in all, spiritually V1, even though we've learned from the first two prototypes. Yeah.
What is like different from your team from that lab? So like one that's they also have about microsatellite. What is like some of the better capabilities or cheaper?
Yeah. So again, Planet Labs, they're primarily focused on like capturing color imagery. So they're looking at objects. We're looking at what those objects are made out of. So we're looking at more on the chemical data side of, I've been doing a lot of that chemical analysis. There are a lot of overlapping use cases, especially within agriculture, because they're also red, blue, green, and a little bit of infrared. So they get a few indices that we're also capturing. But then, of course, we go much beyond that in the sense of instead of being able to tell, oh, hey, here's dry pasture because it's yellow, not green, we're able to tell, all right, here's this X amount of protein in your crop versus Y amount of nitrogen or potassium in the actual soil. So that just goes into a very, because it's still a different application. We're not like competing with them. It doesn't like, there's still a huge need for a lot of that data. But yeah, once we sort of go into that, entirely differently new use cases come into play. Planet Labs is launching their own hyperspectral sensors as well. They're launching 2 later this year, so we might be launching on the same rockets. Who knows? It'll be cool if it does happen. But yeah, those sensors are they do kind of like throw us out of the water. But I guess looking at costs, that does cost them like tens of millions of dollars to build, and this is like a $15,000 thing. Yeah.
So I'm just getting it right. I've heard about hyperspectral online. So like taking kind of wavelengths of light and video and detector like algorithms like figure out the spectrums. It's kind of mind-boggling. Like things you have to take into account.
Absolutely.
Especially like just gas or they track from the ground.
That's right.
Yeah, so that's kind of, I'm doing that correct.
Yes. Yeah. So especially when it comes to like atmospheric level data, like gases and all those sort of things, the ground is of course going to be a lot more brighter and a lot more prominent what we're capturing compared to like it's looking at entire columns of atmosphere. And once we of course look at entire columns of atmosphere, different gases have different densities. They'll be their spectral signatures will be mixing in together. So there's like, we're not building the data science ourselves to actually do a lot of that processing. We're still, working with our customers and working with, I guess, other sciences institutes to actually build a lot of that out with our data, which is why I'm like, let's just build the hardware and put it up there, because that is still easier than building that data science. So yeah, we're taking the easier end of the stick. But yeah, yes.
So you have customers for all of that?
Yes, we do. We've like an entire pipeline of 150 mil in pre-orders that we've accumulated. So yeah, once our sensors start going out, they're already like almost fully booked out. We still keep like capacity available.
Of the phenomenon, is there anything you actually able to mention? I'm thinking things like fluidity. Is there any other agricultural environmental issues?
Yeah, so with this current sensor, not many. But we are, again, as I mentioned, we're really expanding deeper into the infrared range, going into short-wave infrared, which is like 2,200 nanometers. That's when a lot of possibilities really become available, just because, first of all, a lot of that data has not been available, especially in the spectral resolution that we're going at. So even there's a lot of applications that are there are not known because the data hasn't been available to conduct a lot of that research on. Secondly, in a lot of the stuff that I mentioned in terms of the applications that we're currently looking at, that's our focus for now. Mainly because once we start going into, I guess, more of the blue sky is type of things where it's like newer applications that are coming up, that becomes on us as a business. It just becomes a lot harder for us to do while building these sensors. And again, goes more down that data science route where we're like, yeah, again, it's us being hardware engineers, that was too hard of a problem for us to look at. However, we are looking at a lot of interesting things with, again, working with our customers there. So micro, macro nutrients for agriculture, where I mentioned protein in the crop all the way to ground level nutrition. That's something that's fairly new in the precision agricultural industry. So that basically, when maybe not from a farmer's point of view, but let's say if you're a futures trader or a commodity trader, this goes beyond just yield prediction, because you're now able to look at entire nutrition that a crop has, versus a different crop in a completely different region. So that's at least something that comes to mind in terms of just, I guess, envelope pushing applications that we're looking at. But yeah, there's a lot more that we're hoping come out of it, and that's basically our bets. Once we sort of make this data a lot more available, we're betting that there's a lot more applications coming out of it that we just don't know of yet.
And don't get me wrong, I'm all for this, but is there like an element of data trying to see to this, like you're imaging someone, everyone else as well? Is that something or is there regulations around that?
It is definitely something we think about. However, there are, I guess, limitations in terms of how much we can do. For example, let's say a commodity trader is going to be paying us a few $100,000 to go out and capture all the farms of, let's say, Victoria, for example, that will be shedding light on few, I guess, properties or few farmers that they might not be doing so well, and that is, of course, their data that's being given out in a sense publicly, because anyone with enough money can actually go out and buy it. There's not a whole lot we can do there in terms of actually regulating it, unless we go out and audit every farmer that's there or every person that's being impacted by that data. There are a lot of implications when it's from a defense perspective. For example, we can't capture imagery over the US or downlink it unless we get a license from NOAA. They be like, yeah, we can capture our geospatial land. And a few other countries do have similar things like that. Australia doesn't, so any satellite going over Australia can capture and downlink, and there's no regulation around that just yet, unless stuff that's being talked about and that's slowly coming to play, but nothing that's a law just yet. So yeah, for us, it just becomes a thing of good faith where we're just like, is our customer going to use this data for bad or for good? And that is something that's on us, and that's something we have to verify anyway. because we don't want hostile entities to be essentially just because they have money, they don't. It doesn't mean that we have to give access to them, access to our satellites to them. So that's a process that we have to do anyway, and that's something that we're looking to implement a lot of these other ethics into that too. But yeah, being honest, we're still fairly early before we get to that point, but we are thinking about it. Yeah, so pre-orders so because again we're cheaper, that allows us to look at customers who are capturing very large land masses. So if you go out and buy a similar data image, it'll cost you like $30 per square kilometer, not assuming there's a minimum water quantity on it. If you're a customer who's looking at millions of square kilometers, that $30 per square kilometer really scales up, because we're 20 times less. We're offering $1.50 per square kilometer. That just allows us to go for these really large customer sizes. And that's how, if we get 10 of them who are buying millions of these, that's how it sort of really adds up to that entire pre-order book, even though we're still pre-launch fairly early in our I guess, technical / product life cycle. That's just allowed, I guess, again, engineering it from the ground up, working with those initial problems really helped us get to where we are. It was pretty much accidental. But we're happy we're here.
With the sensors you have on the board and data processing, are you able to measure data or get measurements at various depth levels on the about that surface, or like is it essentially stuff that
we are surface level, so it is surface level reflectances depending on the soil types, depending on the clay types, or whatever we're capturing. We might be able to penetrate around 15 centimeters of it. I guess the 15 centimeters mostly comes from like agricultural porous soil. I'm simplifying quite a few things here, but that's sort of different topographies will have different depths, but for all purposes, we're basically surface level, which is why it's surface level of the Earth all the way to the atmospheric column until it reaches our sensor.
And sorry, I have a follow-up. And do you have I guess like the sensor target is sort of like the thing that you're probably constrained on. Do you have like some free time where experts is capturing data outside of becoming things to your own customers? And if so, do you plan to like are you like thinking along the lines of like maybe open source that data and then having like other people like poke around like take, for example, data?
Yes, absolutely. So at least with these two, of the first two sensors, we are primarily looking to do that because we don't have a whole, I guess, because there are first two, the data might be really bad, or it might be what we expect it to be. So a lot of that data will be sort of given out fairly openly. That's what we're planning to do with these first two, and in ourselves, we have to conduct our internal technical audits as well to be like, all right, if we're, especially when again going back to that calibration piece, where you have to capture our own data. I do see ourselves playing a part when it comes to, I guess, open source intelligence. I do see us sort of capturing a lot of the data and sort of making it available there. But there is a huge cost constraint, and there's that entire processing constraint that would eventually become a decision of like, hey, do we capture this for an open source use, or do we have this customer who wants to buy it instead? So it would I guess be a decision for then. But yeah, that's sort of like a dilemma that we I guess do sort of face there.
Please don't be like that. What probably this is the last question I'm asking. You mentioned that there is some amount of regulation around capturing data. Out of curiosity, I'm not like seeing anything here. And how would the US government regulate or prevent you from
Yeah, they cannot in some purposes, but the U.S. Department of Defense is again the biggest buyer of satellite imagery data. Even if we're not a U.S. company, they're still going to end up being our biggest customer, even while we're focusing more commercial use cases rather than defense and some of the use cases, it is unfortunately a bit of an eventuality, at least in the short term. At least in the next 5 years, they're still going to be one of the biggest buyers of that data. So of course, we wouldn't want to do anything to step on the toes. Yeah. For sure. Yeah.
Okay. All right. I think we should probably sort of wrap it up there. Thanks. Thanks
No
so much.
problem. Thanks a lot.
This little thing. There we go. Yes. Sorry about that, everyone. Thanks everyone for coming, and we'll wrap up here. And if anyone's keen, might go over to the Rainbow Hotel for a drink afterwards. I don't think there's anything. If you've got any other, if you've got any ideas for talks or people or companies you think would be great, refer them through. That is so weird. I can turn that off now. But anyway, thanks a lot for coming. We'll see you next time. And I don't know when the next event will be, probably in a couple of months' time. Well, June, well, you'll find out about it. We'll promote it. Yeah. Well, no, we just haven't locked in an exact date yet. Big news coming. Watch this space. Okay, thanks everyone.